Welcome everybody. Thanks for tuning in to my presentation about digital twins. Before jumping into the topic, let's first explore the term of a twin in our context. For this, I would like to use the example of the Apollo 13 mission. The Apollo 13 mission was a mission from the NASA to the moon. On their way there, they encountered a problem, but they couldn't identify the issue. So basically, they sent a message to Earth where they said, Houston, we have had a problem. And then, they couldn't do anything more than that because they couldn't just exit the spacecraft. So how do you identify such an issue? In this example, what they did is they used some help from the sensors or from the simulators that they used to train the astronauts. These simulators were used to train the astronauts, and they adapted them in a way to reproduce the problem that the astronauts had in space. On the picture here, you can see the two simulators that were used, and basically they used the same hardware inside of the simulators as the real spacecraft had. They were hooked up to some computers so they could try out certain things. And basically they adapted them, then they tried to figure out a solution, and then once they had modified the devices, they sent back the solution to space. So what about the digital part? As we saw with this simulator example, we had a kind of real twin, and now we take this real twin and digitalize it basically. This copy or this digital twin can then be used to communicate with the real twin, to basically gather data about the real twin, to communicate with it, send some commands to it, to organize certain twins together in groups, and basically to deal with the real example in a digital context. So what are some sectors where we use this? Basically, everything that has some kind of Internet of Things context has or can use twins. So for example, we can use it in manufacturing purposes where we have some kind of machines and that has some sensors. We can use it in healthcare to represent data in a standardized way. For example, I want to have a digital representation of a heart, and I want to measure the heart rate. So I could model the heart as a digital twin and then have access to the heart rate via this twin. Then I have the context, for example, of a smart city where each building could be a twin, and that twin could then consist of every room, and every room would have like sensors or it would have light, and then I could basically group them together. I could say this is this district, and then I could have streets with entities like cars and persons that also could be digital twins again. And basically, as this example shows, you can model basically everything with these digital twins. And also in data economies, you want to have a standardized way that you can use to exchange data. For example, I have a temperature sensor and I want to share that data of the temperature sensor with other people. They should know what sensor it is, or how they can access that data stream. So that's also a way where you can use a digital twin and the digital twin representation, so it is kind of like standardized. Like with every standard, there are multiple competing standards. So in this presentation, I will focus on the DTDL standard. That's a description language that was created by Microsoft in partnership with multiple industries. And it's basically based on JSON-LD, so it's using JSON linked data. A lot of the web developers might know JSON linked data from websites where you can basically optimize the website for Google or something like that by setting some kind of meta tags. And that's also basically using JSON linked data in the background. And like I said, it's an open source standard. We said that it's a modeling language, so we need some kind of building blocks that allow us to basically create our models. And these building blocks really make it a lot simpler to create these digital twin models than some other standards, because some restrictions are always better than no restrictions when it comes to modeling. You don't want to have too much freedom. That's why with the DTDL standard we have these 6 building blocks. We have an interface where we can basically group together other building blocks. So for example, we have a telemetry block where we can say, yeah, we want to access some kind of data from a device. Like we take the example of the temperature sensor from before. We want to access the current temperature. Then we have properties, so like a setting, do we want to continue like measurement? Do we want to switch the device on or off? Something like that. And these properties, they can have multiple types. So we can have a string property, an integer property, a duration. We can have a map, an object. Basically everything can be a property. Also another schema or interface can be a property. Then we have some kinds of commands where we can communicate with the device. So we can say, oh, please give me the current temperature value again, but not as a stream, but as a response. So I just ask for one value and not for a stream. I can switch the device on or off. I can tell the device to do a measurement every 10 minutes or something like that. So basically, just give the device any command. It's like a function basically, or a method. And then you have some relationships. So when we go back to our smart city example, we have a district, and in that district there are multiple buildings. So the district has some buildings and the building belongs to the district. So we can model relationships between them. Or a house has multiple rooms, for example. Yes. And then we also have the building blocks of a component. And a component is basically a small unit. So we want to have a device, but we don't want to have it consist out of multiple interfaces. But instead we say this device is the smallest possible unit. And then we basically say that's one component. Once we have created one of these models, we also want to have a unique identifier for the whole thing. And generating a UUID would be way too simple, and it would not be really human readable. So for that we have DTMI, a Digital Twin Model Identifier. This model identifier basically consists out of 3 parts. The first part is the scheme. So in this case it's DTMI always. Then the next part is like a namespace or a path. And there usually you just take the domain name, the fully quantified domain name of your company, turn it around. So for example, Tributech.io would be IO, Tributech. And then you basically can define anything you want. The reason for that is that this way you have a lot less collisions when it comes to the domain names. And if there are collisions, they are usually in the same geographical area. So for example, if you would have a domain name with AT for Austria, you would have a collision within Austria, and it would be much simpler to resolve that collision or to even know about that collision. And then in this example we have a device, and the device is of the type edge in our case. So that's basically the part, and then you have a versioning number. Because every time when you model something, you want to have the possibility to have multiple versions of the whole thing. And for this you have this version number here. Here we have one example of a twin file. On the left side you can see basically the model of the twin. We can see that we have some inheritance there with the extents, and in the contents you have your smaller building blocks. And on the right side you have a finalized instance of that model, where we can see the properties, and we have a reference back to the original model via this method data tag that references back using the DTMI identifier to the defined model. On the left side you can also see that each property or each building block has some fields where you can set some metadata, for example description, comments, display names, if the property is writable or not, and yeah, also what kind of schema is used for that property. So what are the advantages now for developers using this digital twin model standard? It allows you to basically represent any kind of IoT device in an abstract way. You don't need to know about every device that's out there, you just need to know about the building blocks and the possible combinations, and then you can work with this IoT device. You can mock the data responses, you can mock server responses, because you always know what is the allowed communication. So it's basically like an open API standard just for IoT devices. You can generate a generic user interface based on these twin models, because you only have to represent each building block, and then you can just basically stick it together and you have a final UI. Then you have this consistent representation of data from the device to the backend to the frontend, because the twin file itself is kind of like a single source of truth for the state of the device. And you can just pass that through all your layers. The standard allows you to basically have some kind of domain-driven design or domain-specific model language, where you can model your model files for your specific application. So it doesn't depend what sector you're in. You can use these building blocks and adapt them for your needs. And also the traceability is greatly enhanced, because if you change something, you immediately get a response if something goes wrong via this telemetry data. So if it's all hooked up together, each change will immediately trigger an error at the telemetry data, and then you immediately know something went wrong. And even afterwards, it's much easier to basically know about what happened due to these changes. If you're interested in the topic, there are two major platforms out there currently that support the digital twins. One is the Eclipse D2 project, that's completely open source, where you can basically talk with twins, create twins, and manage twins. And the second example is the Asia platform from Microsoft, where they also have a digital twin service that allows you to manage your twins. I hope this presentation taught you a bit about digital twins, and it's a really interesting topic, and I think that will come up a lot more in the future. Thank you very much.